This is lecture 4, part 4, and we have a special treat with this part. We are coming to you live from Carnival in Venice. Domino is in full costume. Just as a review, in part 3, we looked at current voltage curves when applied to an electrolyte solution. And when there's an electroactive species present in that solution, there is electron transfer between the electrode and the material in solution. And so you get a discontinuity in the current voltage curve. So as indicated, there is a flattish part of the current voltage curve that corresponds to diffusional current of non-electroactive species in the solution. So this is analogous to conductivity measurements. But when the when the electroactive species undergo electron transfer, that occurs at a faster rate, faster kinetics, and you get a discontinuity and a rapid rise in the current. And there are two linear sections if the solution is stirred. We saw that the transition point, namely where the discontinuity occurs, changes when you change the concentration of the electroactive species in the solution. So this tells you that the behavior that you're observing and the transition is somehow tied to the Nernst equation. We established at the end of part 3 how this relationship applies, but this is just the general statement. We saw that when the electrolyte solution is not stirred, there is a boundary at the electrode-electrolyte solution interface where electron transfer can occur, but beyond which electrons cannot reach the material in solution. So when you reach the correct voltage supplying the energy for electron transfer, that boundary layer is rapidly reduced, giving you the rapid rise in current. But then once all that electroactive material has been reduced, it has to be replaced by material from the bulk, and that requires diffusion. So you get another parallel branch to the straight conductivity diffusion current that delimits a so-called diffusion-limited current. And we saw that the diffusion-limited current is proportional to the concentration of the electroactive species in the bulk solution. And secondly, by examining the currents, we saw that the half-wave potential, the voltage at which the current reaches half of the diffusion-limited current, that roughly corresponds to the standard state oxidation reduction potential of the electroactive species. And what I did not indicate in part 3 is that there's a superposition of the processes or the observations, so that if you have a mixture of electroactive species that are different, the polarographic waves stack on top of one another, and you read the diffusion currents independently of one another, and likewise with the half-wave potentials as indicated in the diagram. So this is an example with two electroactive species, one which is reduced prior to the second. So you would see the first wave naturally first as you hit the voltage, and then the second wave gets superimposed or stacked upon the top of the first one. And then you would get the diffusion currents by extrapolating the linear parts outwards, or the limiting currents outwards, as I've indicated by the dashed lines, and measure the diffusion current with respect to those. If we look at this in practice, the basic setup is the so-called H cell, which you encountered in quantitative analysis. So a reference electrode and an indicator electrode where all the electron transfer is going to take place. The boss, however, is going to point out an obvious flaw. There is a flaw. That does not say paw, that's flaw. And the flaw is that you don't ever want to have current running through a reference electrode like the standard calomel. So there's a basic, there's an improvement on the basic electrode arrangement. And that is to introduce a third electrode which carries the current. So in doing so, we do that little setup. We have the reference electrode in one chamber, We'll have the indicator electrode in the opposing chamber, and then we'll introduce an auxiliary electrode into the same chamber as the indicator electrode. And when you do this, and by carefully arranging the circuit, you'll exchange the current between the indicator and the auxiliary electrode, leaving the reference electrode unperturbed, and therefore its standard reference value will not drift as a result of the chemistry taking place in the electrode. So typical indicator electrodes, they're normally noble metals, so they don't participate in any chemistry directly, they just act as sources or sinks of electrons. The common indicator electrodes are gold, platinum, and a mercury in the form of a drop hanging from a capillary tube. The auxiliary electrode is similarly a noble metal. It's going to be larger in terms of its surface area so that it does not affect the current voltage curve of the experiment. Typically it's platinum, a thick piece of platinum wire, or some wire mesh that can be wrapped around the indicator electrode. Alternatively, you can have a pool of mercury, which is what I indicated in the cartoon. So that little droplet of or blob of silver there represents the mercury pool. Finally, the reference electrode usually depends upon what type of chemistry you're working with, namely the solvent system, the pH, and so on. The common ones are standard calomel electrode and the silver-silver chloride, which are good for aqueous systems, and to some extent, the silver-silver chloride electrode can be used in non-aqueous systems. You would use oxide electrodes if you happen to be working in extremely high pH. Boris is here, and he's drawn us a little cartoon of a very simple setup, and you did this in quantitative analysis, or I did it for you actually this year in quantitative analysis for the electrode galvanic cell experiments. So if I applied a voltage across that resistor, that potentiometer, I could vary it by playing around with the tapping point on the potentiometer. So I attach a battery parallel to the potentiometer that I've indicated here. Boris did not put in the battery. But by sliding that wire back and forth, I could manually pick up a voltage of a given value and measure the current directly. Again, a point-by-point plot. I have here two waveforms, and these are going to be the nature of the experiment. So on the left, I have a ramp with a direct return to the starting point. So this is a special kind of sawtooth, and this would correspond to a typical polarograph or single direction, simple voltammetry experiment, single wave. So again, time is the x-axis, and I've got two waveforms or two repeated experiments side by side on the left. On the right, I have a different situation. I have a more gradual return to the original starting point, and by running the return to the starting point at over a period of time, I can reverse the electrochemistry in a controlled fashion. So I can do kinetics with this. I can actually watch experiments or side reactions owing to the reduction process or oxidation process take place in real time. And that's going to be the advantage of this type of an experiment. So in general, polarography is distinguished by the rate of the voltage sweep, which is generally slow. And by going slow, I minimize the effect of the capacitance on the current voltage curve because the system has time to respond. And it's a relatively clean-ish looking profile of current, a little step. If I increase the speed, the capacitance is going to start to make itself known to me. I'll explain how in a second. But it gives me the advantage of being able to do kinetic studies, namely play around with the rate of the voltage sweep, which determines the rate of the production of the reduced or oxidized species in solution. If I have another reaction taking place in there, I can make those two reactions compete with one another and observe the changes in the concentration, namely the peak heights. So this gives me information regarding the kinetics of chemical reactions. This is more of interest if you're doing PChem or electrode reactions. So when the system is ideal, I'm going to have a forward sweep sloppily done here, but you get the idea. That goes in one direction. If I have the reverse sweep, again, that waveform with the sloping second part when you return to the beginning, it follows the same path. So we call that the reverse sweep. And so in an ideal world, there's no capacitance effects. The electrode reactions are reversible, and so the forward and reverse sweeps trace over the same current and voltage. There's no gaps, there's no funny business going on. On the other hand, if I have a capacitance effect, I actually see separations between the forward and the reverse sweep. And so the real world capacitance does influence the graphical display of the data. There's actually a shift, and that shift to the different pathways is what we call hysteresis. Capacitance also alters the current voltage profile by introducing delays or overshoots in the forward and reverse sweep. So at these points where you're making the sweep and reaching the maximum value, so the arrow at the top corresponds to the forward sweep, which is the top trace in green, and the bottom arrow is the reverse sweep, with the diffusion limiting current actually being at the bottom of the sweep where the orange arrow is. What you'll see oftentimes is a little bit of an overshoot, like a hump, or if you want to call it a spectroscopic peak, that appears in the current voltage plot. So the back and forth sweeps resulting in an IV curve that has these characteristics is called a cyclic voltammogram. So you have forward sweeps, reverse sweeps simultaneously presented on the current voltage plot, and you derive your information from this profile, cyclic voltammogram. It can be a single cycle, it can be multiple cycles. All types of variations give you different types of information. It depends on what you want to get out of your experiment. Most times you get something in a real situation, particularly if it's symmetric, something that looks like this artfully drawn cyclic voltammogram. So this is a freehand drawing, sorry. But if this were symmetric, it should be symmetric if you have electrode reactions that are reversible and you're strictly limited to kinetic and capacitive effects. But the kinetics are the same for both oxidation and reduction. Assuming that it's reversible and symmetric, the peak-to-peak current is proportional to concentration. So in other words, that the top of the voltammogram that looks like a duck to the bottom, which looks like the duck belly or the bird belly, that current difference is proportional to the concentration. To get the equivalent of the voltage at 1/2 peak, the midpoint between the peak voltage and the trough voltage is approximately the standard state redox potential of the electroactive species. For a better drawing or better artwork, I have this from Harris. This is figure 1723 in my edition. But on the upper left, you see the classic reversible cyclic voltammogram. And in the bottom right, that rather elongated, horrible looking thing, like a parody of the one at the top, that's what you get when you see an irreversible reaction. So those are the types of behaviors that indicate the types of chemistry or kinetics that are taking place in the solution. So that concludes part 4 of this lecture, and I see that Boris and Domino are sharing photos of themselves out on the promenade in Venice at this point. I wonder, maybe perhaps you also wonder, where Katie is, the other cat we call the boss. Katie is out in the gondolas in the canals. So all is well, the cats are happy, they're doing their thing.